Everybody for coming here. Today I'm walking you through the identification of Haddad curves, combining logistic regression and maximum a posteriori estimation. Consider this kind of metallic specimen which retains defects irrespective of the manufacturing process. And if we test several of these, spanning many loading conditions and characterizing the size of the defect where the fatal fatigue crack occurred, we get this plot, for which we assume working within linear elastic fracture mechanics, defects regarded as cracks, Murakami's length as the characteristic size of a defect, and the mode 1 stress intensity factor range as the fatigue crack driving force. Amongst many models, Haddad curve allows assessing the fatigue endurance limit, considering the presence of defects. And the Haddad curve is the black solid line that separates the regime of propagating cracks and non-propagating cracks. The equation of this curve is this. Okay. It's overlapping. This one is overlapping. Okay, trust me about the equation. I'm not cheating. Don't worry. Well, delta K, TH, and C, you see on the right is the fatigue crack growth threshold for long cracks, while delta sigma W is the fatigue endurance limit of a defect-free specimen. And somehow these two parameters should be determined. And over the years, many researchers have developed many models to do so, but these models require complex experimental calibrations and basically neglect the previous results from the literature. And needless to say, populating this graph is such an onerous endeavor. No one so far has attempted to determine this curve using the sole data we see here, only the markers, the points, and the crosses. And that's our goal. Let's move to the case study. We consider this literature data set that regards this aluminum alloy. These are the fatigue testing conditions. And the gray line is the reference Haddad curve, whose parameters are these. The former was identified by fatigue crack growth tests, while the latter was extrapolating by these authors from the model, essentially. But let's pretend not to know the gray line. And I gotta say that the defects pivotal to structural integrity are concentrating around the mid region of this graph, because those on the leftmost side are far too small, whereas those on the rightmost side, well, we hope there aren't any such big defects, okay? And potentially, I might draw infinite Haddad curves, but how can I determine the one that optimally splits this data set without characterizing the entire spectrum of defect size, only using with this data at my disposal and assessing the error of the evaluation? Let's see. Let xi and theta be the tested sample and the vector of trainable parameters. The Haddad curve essentially tells us that specimen above the curve should fail, whereas those beneath should run out. And this actually is a typical machine learning binary classification. That's our idea, however. We think that the probability of failure should increase as we are moving upward away from the curve, and vice versa for runouts. So this failure probability should be linked to the sign distance of a point to the curve. And that's where logistic regression comes in handy, because it squashes these distances into the interval 0, 1, thus returning probabilities. Normally, logistic regression is trained via maximum likelihood estimation, which entails building this likelihood function and maximize it. This is the likelihood of this data set. And the parameter of the curve that optimally splits the data set are supposed to be located at the maximum of this function, where the maximum exists. And so this approach in this case wouldn't work. But we can notice that an hypothetical optimizer would be naturally attracted to the yellow region, where the log likelihoods steadily increase around 180 megapascal. And such an intuition suggests that the data set could be almost perfectly split by an horizontal line at 180 megapascal. And what about the other parameter, the delta KTHLC? Well, we examined many papers where other estimates of this parameter were available for similar materials as well. And we encode this prior information using maximum a posteriori estimation, which relies on Bayes' theorem. Posterior equals likelihood times prior over the evidence. And taking the logarithm of both sides, we end up with the log posterior that has to be maximized. By the way, the log prior was derived by assuming independent distribution for each parameter, but still the user can prescribe in principle any distribution over these parameters. That represents our prior belief over these parameters. Let's assemble the log posterior. This is the previous log likelihood. And exploiting the evidence separation of the data set, we let the data dominate as far as delta sigma W goes. And we prescribe a prior that vanishes during maximization. Conversely, regarding this parameter, we gather the results from the paper I mentioned earlier into this normal distribution. Summing these two colored contribution, we get the log prior. And if we sum these contours, the result is really, really cool. Now, the log posterior does have a maximum where the optimal parameters are located. And differently from maximum likelihood estimation, which provides only point estimates, the maximum a posteriori gives the joint probability distribution of the parameters. And marginalizing it out, we can retrieve each distribution for the parameter. And the mode of this parameter, the mode of this distribution, leads to the evaluated Haddad curve in black, which is the optimal one. And also this concurs well with the reference in gray we've seen before. Sampling the posterior distribution of the parameters, we can generate numerous Haddad curves in a Monte Carlo fashion and calculate the prediction interval for a confidence level of, for instance, 95%. And we get the lower and the upper bound of this prediction interval that can be interpreted as the failure probabilities at 2.5 and 97.5%. In particular, the lower bound can be interpreted as the probabilistic fatigue endurance limit for this material and can be used in engineering practice design. That being said, we are ready to wrap up. Logistic regression models the binary classification of the Haddad curve, maybe inconclusive when trained via maximum likelihood estimation and only provide point estimates. Conversely, maximum a posteriori encodes intuitions, hypotheses, and prior knowledge from the literature while training logistic regression and provides interval estimates, according to which we compute the prediction intervals using a Monte Carlo approach, and we can calculate the probabilistic fatigue endurance limit so that this can be used in probabilistic engineering design. You can email us for further questions. And I also invite you to visit our research group website. Here we go.